Okay. You can see my screen, I assume?
Yes.
Okay, so lecture 2 will be case studies. Maybe I will go through some of them a little bit fast, as I have to finish by 3. So I've already talked about this, that we make different kinds of products where we convert the raw materials to products. We need to know which product to make, how to make, when to make, and so on. So according to the classification that I have given you before, I'm listing some of the products. This is not a full list, it's just some list. Under molecular design, the most popular are the refrigerants, surfactants, fragrance molecules, polymers, solvents of many types. Solvents are not just for separation, solvents are for cleaning, for product delivery, for reaction synthesis, a lot of different things, active ingredients, and many more. So in all these cases, we are looking for a single molecule. Note, however, that single molecule does not mean that all the properties are pure compound properties. To design a solvent, we need also mixture properties. Okay, so just because it's a molecular design does not mean that it is only pure compound properties. Then mixture is a mixed refrigerant, then it's a blend. Fuel, there are different kinds of fuels, gasoline, diesel, kerosene, jet fuel. And also I didn't put here oils, but edible oil. Edible oil is a very good blend design problem. Lubricant, it's not just a single compound, it's a blend of chemicals that is a lubricant. Instead of a single solvent, one can use also a solvent blend. Process fluids, one may want different kind of mixtures. So maybe I have a mixture in my process, and the process, the fluid has to go through a pipeline, and it is very viscous. So can I add something to make it less viscous? So that is also a mixture design problem. So aroma, fragrance, and many more. And formulation design, the difference between the mixture blend design and formulation design is that in a mixture blend design, all the chemicals that we will add are liquid, and we are mixing liquids to make a liquid blend. In formulation design, our final product can be a liquid or can be an emulsion, and the different components of that product can be solid and liquid. So we mix them together to the final form. So if we have a solid, which is the active ingredient, then we need some solvent to dissolve it. So then our product will be liquid, and then we put some surfactant to make it emulsion. So depending on what kind of product it is and what are the different ingredients, those ingredients will have different states. Also in webinars 3 and 4, we already looked at refrigerant design and chemical substitution, which are sub-problems of chemical product design. And we have developed special tools for refrigerant design and chemical substitution. I've already talked about this before. So we have the preliminary step where we convert the needs into product attributes and then their values. Then we formulate the CMD problem. Then we decide which way to solve it. And then finally, we do verification. Okay, so here I will just explain a little bit more. So in the center is what you see, Pro-CAPD. It can solve for molecular design problem. It can solve for formulation, that is blend and mixed and liquid formulations. And then we say functional products as emulsified formulations. For some of them we can do device, we just have 2 examples. There's no method there. So the methods are here in formulation, blend, in liquid, in molecular design, and in liquid formulations. And what you see here are the templates. These are templates for blends and mixtures. These are templates for molecular design. And then there is database and other tools. And then that's the inner. Then we have databases, solution methods, property models, and property function calculation routines. And all of these require different kinds of database. Database has database of chemicals, organic, lipids, ionic liquids, aroma, amino acids, all of that. Design templates have molecular design, mixture design, solution with optimization, solution with decomposition method, different kinds of solution techniques. Property models have different kinds of property models, and functional properties have different kind of functional properties. Functional properties means like if I put a paint on a wall, what is the time it will take for 25% evaporation of the solvent, 75%, 95%. Those are very important parameters for paint formulations. If we design a microcapsule for controlled release, then the release as a function of time needs to be predicted. So that is also product function, okay? So these are different from these property models. And you will see later solution of problems through different features on ProCAPD. One other thing is that in order to make this product as versatile as possible, we need the models of the product as well as the property as versatile as possible. So we made a versatile product process model. Different color here indicates different kinds of model. So molecular structural model, then property model, a process model to check the quality of the product, performance of the product as a function of time, sustainability criteria, economic, environmental. So depending on the problem, we can retrieve the model equations for each of these and put them into our general mathematical problem formulation. And then this is the problem that we want to solve in different ways. So this is one step in trying to make this as versatile as possible. And the idea is that with time, we'll have more and more, we will have a library of models in each of these colored boxes, and that will then allow the user to get many more models. And we have talked about this already, so I will skip this, and I will directly go as the first example, surfactant design. So step, why is a surfactant needed? It is the active ingredient for ultraviolet sunscreen lotion, which is used in emulsified form. So a surfactant is needed to create that emulsion. Surfactants are large molecules. So what we are doing is we are giving a backbone of the surfactant that is part of the structure we give, and we ask the molecular design to fill out the remaining part. This kind of problem can be formulated and solved in the software. So we want to minimize the toxicity of the surfactant. We select the groups that should be used to find the molecules. We give the backbone. You will see the structure of the backbone later. We give the upper and lower bounds in terms of property constraints and structural constraints. And we list the properties that are going to be made: toxicity, with respect to a fish, fathead minnow, solubility parameter to look at the solubility, cloud point to look at some of the emulsion related properties, flash point for flammability, liquid molar volume is also needed for the emulsion related properties. So then the equations we extract from our library, the equations we need, and these equations depend also on the kind of molecular structure we are making. These are the structural parameters, and these are the property model equations, simple group contribution equations. So, but if we count how many equations we have actually 1,324,764. So 1.3 million, let's say. And we have 1.28 million variables. So it's a large problem, but it can be solved very fast directly with the optimizer and also by generate and test. So then the model is solved with GAMS, and this is the backbone we have given. And to the backbone, there is a point here, and there is a point here, and there is a point here, where CMD will add additional structures. And then it created this molecule, which satisfied all the properties. It can be done by hand, of course. If we give you the backbone, then manually you can add things here, add things here, add things here. Go to a property prediction model, which is group contribution, and you can have that in Excel and calculate the property. So manually it is possible to do, but by the time you do, one will do 3 or 4, the computer will test everything that is possible. So that's a simple example of surfactant design. And then one takes all the different molecules that are generated, more than 50 are generated, and then one can do more detailed calculations. Another example is polymer, and you can see here that these bottles are made of cork or natural rubber. And the idea is that because they are not really very good in stopping either gas from coming in or going out, so can we devise a membrane-based kind of polymeric stopper that will stop the gases coming in and going out? We don't want that. So can we do that? So that can be a problem formulation like polymers. One could also try to find, can we find a replacement for nylon as a fabric or Teflon for the frying pan? And so all of those can be formulated quite easily in polymer design example. I'm just showing you the case of the cork, the stopper. So first formulate the problem, repeat unit identification. But once we have identified the repeat unit, we will then go into molecular simulation to find the chain length and the chain size to see which is the best chain length of the polymer that will give us the best properties that we wanted. So we do the simple molecular design, and we identify the chain length, which is something like a C3 polymer repeat unit. And then once we have found that, then we want to find the amorphous rubbery glass transition temperature should be less than 360. The medical container may be agitated, so the dielectric constant should be less than 2.5, low water absorbability and low permeation to air. So with all of these and then the structural constraints given, we find out that this with three carbon, a hydrocarbon, has the best properties. But this is just one repeat unit. So then we want to see how many repeat units are needed to optimize the property, because polymer is not just one repeat unit, but a large molecular chain. So for that, we need molecular simulation. And by molecular simulation, it is possible to find out what is the ultimate highest carbon number, after which, let's say, the specific volume will not change, or the permeability will not change, and things like that. And then we are able to find out what is the best polyisobutylene with what is the highest carbon chain that will give us the best properties of the cork, of the stopper that we are interested in. So this kind of problem can be solved. I won't say easily, because in order to do this molecular simulation, to solve the problem, we didn't need to do that, but to develop the model as a function of the number of carbon atoms for each data point needed 6 weeks of simulation. So then you can see how long it took to do this curve. But once we have the curve, then afterwards, we can just use the experimental data to predict for others. But the first one needs 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 times 6, 66 weeks just to do this curve. So it's not that simple with respect to time, but once the data is generated, and if they are accurate, then it gives very good results afterwards. Solvents, as I said, solvents are not just for separation, as you see here, separation, but also synthesis, also in formulated products. Solvents are used to deliver the product. So all delivery mechanisms have solvents. The idea is that solvent will deliver and vaporize. And then for washing, cleaning, so there are different applications. And then under each of them, there are different types of application, and then different functions. So then we can see that based on this, solvents can be used for reaction synthesis, for mixing, selectivity, reaction rate, scalability, isolation of and separation, solvent extraction, distillation, cooling. Also for reaction, it can deliver the solute, that is the reactant. It can deliver the reactive agent. It can deliver heat, take off heat. It can have many different functions. As I said, product recovery, easier operation, cleaning, washing, safety, all of these solvent has a role. So if just in product design area, just solvent design can cover a lot of applications. So this is a typical example for solvent-based extraction. The example is for vapor-liquid separation. So if we have a mixture of acetone, chloroform, or ethanol water, or MTBE, methanol, these are all binary isotopes. And so in a single distillation, it is not possible to get two pure products because the driving force at some point is 0. So if we start with a feed here, we can get this pure product and this product, but never this one. So that means that, or if we start from here, we can get this pure product and this isotope, but never this one. So if we want this pure product and this pure product, we need to break the isotope. And that's what the solvent does. So the solvent takes the other compound. We get pure compound this, the solvent will take this one, and then we will have to recover the solvent. So this is the extraction, this is the solvent recovery. So which is the solvent that will do that? So then we can think of, then as soon as we decide which solvent, we also decide whether it is vapor-liquid separation, that will be extractive distillation, or liquid-liquid separation, that will be liquid-liquid extraction, or solid product recovery, that is crystallization, or gas removal, so absorbs a gas from a gas stream. all of them will require a solvent recovery column. So what is the best solvent? Solvent should not go out, cause problems, should require less energy. So there are many things that can be added. So let's see what kind of properties would be needed. So what you see under E is essential, D is desirable. So we must have these essential properties. And in addition to that, if these properties were there, it will be desirable. So we have liquid extraction, extractive distillation, isotropic distillation, solid, and gas. And these are the solvent properties. And then with respect to environmental health and safety, it is this. So which means again, that as soon as we know the need of the solvent, we can convert the need through this table into properties and then the property values. So that requires a lot of extra work, but also the kind of question that was asked about adhesive. So one could make a table for adhesive, and then one could say, what are the essential properties and what are the desirable properties for adhesives. So then it would be in future very easy to formulate as adhesive design problems. But I think, as I said, in the literature, it is already possible to find that. So now let's go back to the problem of acetone chloroform. Acetone is here, chloroform is here. It forms an isotope, and we would like a solvent that would extract the chloroform from the acetone. So here is the distillation column mixture. So we have the feed, we have the solvent, recycled solvent. We put it into the first column, acetone goes out, solvent takes the chloroform, then chloroform goes out and the solvent goes back. And if you want to make the lines on this diagram, so this is the feed and the solvent. Feed and the solvent is mixed to have the mixture here. And then this mixture is separated into A, which is this product, and B1, which is this product. This B then goes into the second column, and we get our acetone here, and the solvent is recycled. Now, as I said, this, you can see here, I said this is a desired distillation boundary, because what it means is that if this curve is high up and touching this line here, then the higher this touching line is, the less solvent we would need, because according to the inverse lever arm rule, the amount of solvent needed is this. On the other hand, if there was a mixture that was like this here, then this line had to be like this. So we would need much more solvent. So immediately we can see that if we can get a line like this, we will need much less solvent and the process would be much better. Together with it, if it requires less solvent, then also the separation will be less in the solvent recovery, so which means that energy required will be less. So a lot of things will depend on how this curve is, and how this curve is how we generate and find the solvent. But to get this curve, it's not pure compound properties, it's mixture property. If we go back here, we see that for extractive distillation, we need the solubility parameter, we need boiling point, we need melting point, we need vapor pressure, we need phase split. So all of these things we need high selectivity, we need high solvent power, the isotope should be broken. So all of these are in the essential and desirable properties. Okay, so, but on the other hand, so here in extractive distillation, we put phase split, it needs to check the phase split, but it should not split the liquid into two phases. Because in extractive distillation, it will be one phase. But in liquid-liquid extraction, phase split is needed, but it actually needs to split the two phases, because that's the basis of liquid-liquid extraction. So the solvent here and the solvent here is totally different. Okay, so then we see that already, that if we can find a solvent that will match this one, our process design is already done, and we know that that will be the best solvent. And it turns out that when we formulate the problem with boiling point, melting point, solvent power, selectivity, should not form azeotrope, and other EHS properties. So you can see this is the pure compound property, this is mixture property, phase equilibrium property, pure compound properties. One hexanol comes out as a solvent, and this one hexanol gives the desired solvent boundary. And the one that I said would not be very good would be benzene, where the solvent boundary is much lower. Okay, so already if we analyze the problem and carefully give our problem definition, all these things will be very good. And then one can do the simulation afterwards to confirm that. So similar solvent design problem can be to recover ibuprofen. First, ibuprofen is created in a reactor, and then a solvent is needed to recover the ibuprofen from the reactant mixture. And then we need to put anti-solvent to crystallize out the ibuprofen. So first we need to do cooling crystallization, which will take the solvent will take the ibuprofen out of the reacting mixture. We will cool it. Some solid will be formed, but not too much. Then we, in order not to go too low in temperature, we will put an anti-solvent, which will then do more crystallization. So it is called cooling as well as drowning out crystallization. So in the first case, what we want is the solvent. This is the saturation curve, temperature against composition. Anything above the line is all liquid. Anything below the line is liquid plus solid. So if we can take this line as far to the right as possible, would be the best solvent when we are doing the first step. But we should not take it too far, because we also want to lower the temperature and get some solids out. So what we see is that compared to the literature example for which data could be found, a solvent is found that is a little bit to the right. And then if we start, let's say from 328 and go down to 308 or 303, we get this amount of solid. We get less solid here than with the previous solid, but then we cannot recover as much of the ibuprofen from the reacting mixture. So there are optimization issues here, but after this, the next step is very important. So if we are here, we now want to put an anti-solvent, which will take the curve to the left so that we can get more solid. And that is what an anti-solvent would be. So first with this one, we come here and we get this solid, and after that is liquid. But when we put this anti-solvent, this curve will go here and we will get more solid. And so this is the new one. So if we had only the solvent, that is this solvent, it would be here. But because we have a new anti-solvent we put, and the anti-solvent is here, we get now much more solid coming out. So this is very common in pharmaceutical and food industry to add solvent and anti-solvent. So as long as we can do the solid saturation curves, we can predict how much solid can be obtained, and we can design the process. So you can see here that one process is to make the solvent, another process is actually the crystallization process to obtain ibuprofen, where solvent, our product, is used to get it. So even the ibuprofen is the drug product, and this one will be feasible or not, depending on whether we can find solvent and dissolvent mixture. Now I go to blend. As I said, if we have a vector of target properties, it is unlikely that a single molecule can match all the target properties. So in this case, we divide the, we take more molecules and we make a mixture that is more likely to satisfy a vector of target properties. So the identities of chemicals and the relative amounts in the final mixture blend are unknown at the start, but the molecular structure of the candidates are known. And the candidates are all liquid. So when we mix them, we have liquid. So this is also called tailor-made blend design or fuel design or lubricant design. We tailor-make according to the requirements. The general workflow is still the same. We formulate the problem with respect to properties, with respect to constraints models. The equations may look similar. We then find instead of the groups, we find the molecules. Then we formulate the blend design problem instead of the molecular design problem, and then we do the verification. What is different is the methods and tools used here and the information flow here, because the models are different, the data are different. And as I said, that these problems are very similar, but for each problem, the models and data are different. So even for blends, when we come to blend for gasoline and for diesel and for kerosene or jet fuel, for each of them, the product attributes will be different and the property values will be different. So if we go to gasoline, then we come here, we get the gasoline attributes, and the gasoline will have these target properties, and usually the gasoline will have mainly alkanes and some alcohols, and then we have the target properties, and then we do this. If it is jet fuel, it will be another set, even though the steps to solve the problem are the same. So database is very important here, and the corresponding models are very important here. I will show the example in this case for jet fuel, but we can see. So there are different ways to do the problem. We can say what MI is main ingredient. And main ingredient could be that we have a base oil, and then we want to add to the base oil to improve its properties. So take, for example, a gasoline that you will like to use in your car. And we could say, well, if the higher heating value and some RVP, read vapor pressure, if these were slightly adjusted, the gasoline will go a few kilometers more per liter than the normal gasoline. And it will do less damage to the environment. So that is possible to formulate through changes in these properties. And once we have done that, then we take the original gasoline as it is available and add some additives and say, this is a better one. Unfortunately, at this moment, these additives cost higher. So the price of the gasoline would be higher, but it is a better gasoline. It can be shown. Also, one could directly find the compounds that can represent the main ingredient, because the actual gasoline contains hundreds of compounds, can be represented with 5 or 6 compounds against which we can do experiments. So that is also possible. So we can find the compounds that will represent this, or we can take a mixture and add more things in it. So problem again is similar as before. We have an objective function, we have property constraints, mixture property constraints, and model property constraints. Pure property, because when we select which compound to take, then some pure compound properties can give us an idea of which compound to take. And then the mixture are the mixture properties that has to be satisfied, and process model constraints are the functional properties that have to be satisfied. So the mixture pure property means if we are looking for some molecules of carbon numbers of molecular weight 110 to 120 with certain boiling points, then boiling point could be a constraint to add. So like that. I will just skip this. This is on how to solve the problem. So then we have a step-by-step level 1. This is using a decomposition-based algorithm. That means we divide the big problem into smaller sub-problems and solve each sub-problem. So each sub-problem, then the simplest sub-problem has the biggest number of alternatives. And then gradually, as we go increase the level, we have less and less number of alternatives until we have only a few alternatives, and that we can solve to find the final solution. So here is where we do the final nonlinear optimization. We do the linear optimization. Whatever mixture we make, the mixture has to be stable liquid, that we check the stability, and we do the pre-screening and pre-selection of the compounds here. And that's how it is. Level 1, level 2, level 3, first it does for binary, then ternary, like that. So that's the idea of the decomposition. Oops. So first we solve the subproblem 1. We have a number of alternatives. Then we look for stability that reduces the number of alternatives. Then we look at the mixture properties that reduces the alternative. And then we use the final nonlinear model that reduces and helps us to find the final solution. So the kind of properties we need, again, we have converted the needs to target properties. So if we are looking for gasoline, these are the target properties we need for jet fuel, for diesel, and also for lubricant. So this is the extra word that is needed to create the knowledge base. And then the list of property models. And then the values, upper and lower bounds. So these are also what we are giving. Where did we find them from? It is possible to go to some handbooks on gasoline, diesel, jet fuel, where they give the standard values against which a product can be sold. So we have taken those. And so then let's do a jet fuel problem. So we have taken SPK fuel, which is already available, and then we are going to add additives to make the fuel better. So ability to be burned, safety, these are the needs. We convert them into target, and then the target values and the units are given. So this is coming out of a knowledge base, and it is a lot of work to create this knowledge base. Then we have to generate a list of additives from which we can take to create the tailor-made blend. These additives we created through CMD. So in CMD, we said we want molecules with these properties, generate for me hydrocarbons like this. So it generated all these hydrocarbons. And then these hydrocarbons then would be used in the tailor-made jet fuel. And then by solving it, first we had 54 alternatives, then it reduced to 11, then 7, then 6, and finally 4. And then these 4 were tested, and the actual values, higher heating value and viscosity, CO2 emission, RVP, they were actually measured in the lab. And they were found to be quite good. I'm not sure if anybody would put that on their jet fuel, but at least we found a better fuel than one could find as the base fuel. The gasoline and others are better, but I don't have time to go through all of them. So this is what we found. Ability to be burned, yes. Safety, flashpoint measurement. It was not considered because there was some problem with the experiments. All these things could be done. The next one is the formulation design. In the formulation design, the idea is that we have an active ingredient, which is usually solid, and then that has to be dissolved in solvent, and then the active ingredient together with the solvent then will need a color, will need some aroma and other things. So the idea is that usually people will have different, let's say, containers, the chemist or biochemist, whoever will make it, and they will take from different boxes or containers, different chemicals, mix them together, and then look at the final result. And if it satisfies, then they have the product. If it does not, they go back. So we have generated exactly the same thing with computer-aided molecular design or formulation design. So the first task is to find out which of those additives can be taken, then which active ingredient to take, which solvent to take, which additional additives to take. These additional additives will improve the quality of the product, and then we have the base formula. Once we have the active ingredient and the solvent, here it is very important that these two together show that it is always a liquid mixture, and then when we add this, it is also a liquid mixture. So stability test of the mixture is very important. And then to find out which original compounds, single compounds to take, consider in the mixture after we have found the active ingredient is shown visually here. So let's say if the green dot is our target property, and these are 3 properties, and each of these red dots are different chemicals. So obviously, if we join this and this, we don't pass through this one. But if we had one here and one here, if we join them, then we pass. That is a binary mixture. Also, if we join these two, and then let's say that we had some, we join these two and we come here. And I think I didn't put the right box color here. So let's say we take these two and come here, and our actual target is somewhere here. So then we can see that by taking this binary mixture, we come here. By joining this with the binary mixture, we will come here. So that would be one way of doing it. Another way would be taking these two, come here, taking these two and combining it with these two, we will come here. So there are different ways we can do it. What this diagram will tell us immediately is which are the combination of mixtures that at least one compound will have a property value higher than the target, another will have at least lower than the target. And if that is happening, then by combining the two, we will always hit the target. And the other compounds can be depending on whether they improve or not. So that's the initial way of finding the mixtures. Then once we find the mixtures, we do the stability test. If it is curve B, it is stable. if it is curve A, it is stable up to this point, and we should not have curves C and D. So those mixtures we will eliminate, and we will have the ones that we want. Then once we have done that, and we are sure that the mixture is stable, then we add the additives, and then we check after adding the additives whether the color is what we want, the smell is what we want, and whether it performs the function that it wants. Then we do the experiments or design the experiments, and based on the design of experiments, we suggest what experiments to be done. And we get the final solution. So very quickly, I will go through insects repellent as a spray. So there are different problems we have solved, but I will just very quickly go through this one. These are on the left, the desired criteria we would want. It should be effective against mosquito, long-lasting toxicity, and so on. These are converted to actual target properties, and the target properties are given values. And then based on these, then we go to the database and look for active ingredient. We select one, picaridin. And then based on the picaridin, we find out which solvents can dissolve picaridin, not single solvent, but solvent blends. And for each solvent blend with picaridin, we do the stability test, and we find out that these solvents are good, also with respect to cost. And so initially we started with so many, and then gradually we hit one, which is this. And then one can do the design of experiments and all the different tests one needs to do in order to validate the product. Many of them can be validated with experiments, or we have already done with model, but appearance, stickiness, those are very difficult to do with model. It has to be done by actual experiment. And also these ones. So what we found out was, after doing the actual experiment, these were not satisfactory, but it was very easy to fix it because one just had to add a little bit more of the fragrance, and the pH was too low. So we had to make it a little, pH was a little bit too high. We needed to make it a little bit too lower. So bring it closer to 7. So a little bit of acetic acid was put, and everything became very fine. So this is what was done. And this product was experimentally verified. So what it meant was that we gave a formula, and then through experiment, we fine-tuned the result. And then even shelf life was tested. And it should be a single liquid for more than 6 months, and it was. And this is the final formula. In the same way, one can do emulsified detergents and things like that. I will not go through this because one needs to go to emulsions, and it can be oil in water or water in oil. So I will skip these, but actually the solution of these are given in slides 62 to 77. And you can see this afterwards. So finally, I want to say that this emulsion, one thing is very nice, and it is called the fish diagram. In this fish diagram, if you want to make an emulsion like a margarine, you need to put surfactants, and the temperature should be above the fish. Then you will get the margarine. If you are below the fish, you will get liquid-like detergents. If you want to make creams and things like that, you need to have a lot of surfactants. So like this, you can get any kind of product. So in conclusion, I will just put this in the screen, and I can see that Andre Bardo is looking for the link to join, and I will send him the link. If you have any questions, please let me know. Do you have any questions? Okay, so while we are waiting for Andre Bardo to join, let's see if there are any questions. I'm sorry, I probably went through too fast. There is a question. Please ask your question. Yeah. Dr. Wang.
Hello, hi, Professor Gani. Can you hear me? Yeah.
Yes.
Okay. So my question is, sometimes with this formulation design, like the last example you showed, like emulsion design.
Yes.
With computational tools, sometimes it's very difficult to predict the properties of those complex systems accurately, right?
Yes.
So my question to you will be, like, yeah, I can say that, okay, we use computational tools to facilitate the design of the products, but at the same time, material prediction, like properties prediction, is also a very challenging problem. So in your view, like, what are the existing tools for this kind of property prediction? Are they good enough, or?
Actually, that's why in our toolbox, the emulsified products is still based on database and correlations. Because just as you said, we are not convinced that how predictive those models are. So we can make some initial decisions, for example, with respect to selecting a surfactant or selecting some additives. But when we want to do the overall verification of the product properties or functions, we cannot do it with models now. The models are not accurate enough.
I see. Thank you very much. Yeah.
So we can calculate, for example, the pour point, and then the solid formation, and the emulsion point, the critical micellar concentration. All those things we can do.
Yes. Yeah.
But they do not solve the entire problem. They just help us to eliminate some candidates.
Exactly. Yeah. Yep.
So,
thank you.
Much more work is needed in this area. So that's why we have concentrated on the molecular design, the liquid blends, liquid formulations, because those we can do more reliably.
Yeah. Yeah, exactly.
And emulsion is a challenge. We have to do that. But a bigger challenge is the emulsion structure.
Yeah.
Because the structure of the emulsion also can change the properties. And So there are quite a lot of things to do in that area if one is interested.
Got you. Thank you very much.
Okay, so I see that Andre has joined. Thank you, Andre. Sorry, we forgot to send you the link. Are there any questions? Okay, so we will hope that you will have more questions afterwards to Professor Bardo, and also after the software demonstration and problem solution. So I will let you start, Andre, right away, and you can give your background information.
Okay.
You will need to share the screen.
Yes. You see the PowerPoint?
Yes.
Okay. Do you see a pointer?
Yes.
Okay, then I could not be more happier. Okay.